I'm going to come into the nitty-gritty of ChatGPT. So what I want to really talk about is what exactly are the names in this whole business. That is, what does the GPT stand for? I try to make that more transparent. What does generative mean? What does pre-trained mean? And what the transformer means in this context? And how it all fits together and what it does in terms of what we mean by these terminologies, and give you examples of what goes underneath all of that and what produces the limitations and the strengths of this kind of model. So that's the main purpose of this talk. It will have two parts. This is the first part where I talk about the generative and the training part, and the transformation part I will talk about in the second of my talk. I don't want to make these talks too long. It will be around 10 minutes. Behind the ChatGPT itself, there is a GPT-3. Obviously, that means there was a GPT-2 and GPT-1 earlier. So this is the third reincarnation of the GPT, and ChatGPT is the GPT-3 with a component that talks to people, in the sense that it has an input where people can actually speak in sentences, and it gives you back answers also in sentences. So the GPT itself stands for Generative Pre-trained Transformer. So let me explain what that generative part is. The task for the generative part is to generate a mapping from a low dimensional representation space to a higher dimensional sample space. Now that's a mouthful. So what that means is you have a vector z in Rk, and you want to produce a function g. You want to create a mapping g which transports that z vector into Rn, where n is generally much greater than k. So essentially you are moving from a lower dimensional space to a higher dimensional space through this mapping. So that's the secret sauce of that G. That's what it means by generating. Let me explain what exactly that generating entails. This is a different version of the white Obama problem that I explained in another of my talks. So here I want to generate that G function, explain what the G function does in this context. So here is Professor Vijay Subramanian before that G transformation, and Vijay Subramanian after the G transformation. So it's really a case of OMG. Now, what I have done here is taken out a blob of his face and then asked the GPT, or the equivalent thereof in the space for regeneration in pictures, to recreate the face based on that information that we have in there. So notice that unlike the white Obama case, this is taken out a chunk from that picture, and from the rest of it try to guess what that picture looks like. Now the problem is exactly the same, namely when it recreates the face from the rest of it, it changes the person's race. So Vijay becomes a white person, or close to a white person. His color get whitewashed. you're wondering what Vijay Subramanian really looks like, this is what his picture looks like. This is actually taken from his homepage at the University of Michigan. So by now you should be convinced that the G is the magic sauce in our GPT. That's the generating function. So how exactly does the G transform the lower dimensional vector into a higher dimensional vector? It basically does through training. What training means, it is given lots and lots of data, not necessarily of the same stuff, but of different stuff. In our case, think of it as it has data on lots of different faces from all over the world, and then it uses that information to convert Vijay's face from what it shows versus what he probably should look like. So that's what the training is all about. So what happens, roughly speaking, if the original data set is smooth, that is, in a calculus sense, by that what I mean is that all the functions are differentiable, twice differentiable, and so on, then when you transform things from a lower dimension to a higher dimension, it resembles the reality reasonably closely, and therefore there is not a fidelity lost in the process. However, if there are changes, abrupt changes, or changes that are not very smooth, then the thing breaks down. And that's the general problem of any kind of generative process. So when we pre-train a model, exactly what are we doing? The generator approximately captures the reality. What that approximately really means is that a generator produces a probability distribution over the vectors in the sample space and assign higher probability to the more likely vectors from the data set that has been trained on. So essentially it produces probability distribution. So one part of the face, maybe it will say, okay, it should look like this, and we are going to produce the next image by the highest probability that I think a picture should look like. So we set up a penalty function for the mistakes the model makes, and if your training set has biases, this process will not only retain that bias, but it will amplify the bias, because all these models produce some sort of a Bayesian prior to posterior kind of probability distribution. So the final output will have all those features and biases embedded in them. GPT and GAN are two kinds of models that are floating around. Roughly speaking, GPT is for languages and GAN is for pictures and movies. So their architecture underlying them are not quite the same thing, although they share some properties in terms of how these things are generated. Namely, they are generated through this expansion of an underlying model of a lower dimension to a model which are of higher dimension. So in that sense, they are similar, but otherwise the way they work are not quite the same thing. So the GPT as such cannot be considered a GAN. GAN is an adversarial model where you essentially take two sets of inputs, one real, one fake, usually called the noise, and then you mix them together, and then you look at the output and examine whether the output can be recognized as real or fake. So given that it produces a mixture and we want to extract how often our model is right, that is the principal function of a GAN model. GPT, on the other hand, looks at in a different way, in a different kind of structured way, which can be thought of as a sequence, could be a time sequence, doesn't have to be a time sequence, but nevertheless a sequence. Let me take an example. This is a famous example from Goodfellow and others, wrote a paper in 2014 where they argued that this kind of generating noise plus signal and mixing them up can lead to a very, very bad kind of result. And this was their example. They have several examples, but this is the famous one. So they take a picture of a panda and then does the identification. Okay, so the model identifies that as a panda with nearly 60% probability. And then it adds what the authors call a nematode. And it's basically a noise into the system. And then the noise is not added one-to-one to the original panda picture, but with the probability, with a weight of 0.007. So the noise itself is a small component to the original signal. Now, the output is then submitted to find out what kind of animal it is. The animal identifies the whole thing, the end product, as a given, comes out with 99.3% confidence. But if you just stare at it, you see that it doesn't look all that different visually from the first picture of the panda to start with. So adding that bit of noise, it misidentifies the panda to a completely different animal, which we normal individual humans would never make a mistake of this as being a given. So what this illustrates is the following. This illustrates the kinds of problem that ChatGPT has. For example, when it gives answers to questions, it confidently bullshits about the wrong answer. Essentially, you can say it does not know that it does not know. In reality, that's the wrong thing to say because it's a model, it's a series of numbers. These models have absolutely nothing to do with the language per se. As in our second talk, I'm going to explain why. It's essentially converts everything to a series of numbers and then it retrieves another set of numbers. However, this brings us to another phenomenon that we know of humans. That's the so-called Dunning-Kruger effect, where people who are ignorant don't really know that they are ignorant, but they are very confident about their answers. And this is the same kind of deficiency that ChatGPT suffers from. Now, the second question that arises from all of this is, are these pathological examples that I mentioned earlier with whitening of Obama or completely misidentified the animal, are they at all relevant for what the model that we have at hand? It depends on two things there. Number one, it depends on what kind of transformation that the models use. In the paper of Goodfellow, the transformation they use is logistic, which is fairly linear in most parts of the model, and therefore it has certain characteristics that essentially linearizes the bulk of the distribution. And therefore, when you consider more nonlinear structures, it may not be as relevant. The second, it also depends on the number of layers that a neural net has. So generally we talk about, for example, deep neural nets. What exactly is meant by deep neural net and how is it different from, as opposed to say, shallow neural net? A shallow neural net, or the original kind of neural net that was introduced, was known as perceptrons and so on. They only had one layer. A deep neural net has more than one layer. That's it. There is nothing else in a deep neural net. So it could be one, or it could be 10,000. Today, we are at the other end. Namely, we have thousands of layers in a model. And the reason why we can do that, which we couldn't say 30 years ago, is because the computational power has increased tremendously. There has also been another significant development in 2017, and that is the introduction of what is called the actualization of the model of that was introduced in 2017, that actually in one single stroke solved a lot of the problems. It cut the proverbial Gordian knot to make the model simpler, yet became more powerful. And that's something that I'm going to talk about in my next talk. But here, let me point out the picture that appears at the bottom. These are all individuals who don't exist. So these are fake people. In 2014, the fake picture generators were producing the pictures in black and white, the one that appears on the left. By 2015, we had reasonably looking color images, but they were not very sophisticated. As you can see, you can clearly see the pixels on them. It doesn't quite look right. 2016, it got better, and 2017, it got really, really good. Even if I blow that picture up by scaling it up to a 1048 by 1048, you will not be able to tell whether that's a real person or not. So that's how much advance we have made in just 4 years. And the development that we see in large-scale language models nowadays, they are the product of that particular jump in that process. And that would be in my second part of the talk. To summarize then, we have talked about the generative process. That's the G part of the GPT. Second, we talked about the pre-training of the model a little bit with the data. I'm going to talk more about that. The part that we have not talked about is the transformer part. And that will be the subject of the next part of this talk.